Very good afternoon, dear students. Today we are going to discuss about the categorization and the classifications of different types of turbulent models which are going to be used to solve any kind of a computational fluid dynamics problem. Okay. So, my dear students, as we discussed in our last lecture about various, the theories or the concept related to the turbulency which are existing in your fluid flow whenever a fluid is passing through any surfaces. Okay, so how to solve that turbulency, how we can capture that turbulency in any kind of a fluid flow region. So to solve that particular problem, we have different types of turbulent models are available, and based on which our problem, based on our fluid domain, we can decide which type of turbulent model we can use to solve our that particular problem in computational fluid dynamics. Okay, let's move to our next slide, and I hope you understand all the basics about this particular, and hope that again to revise the fundamental of this fluid mechanics. Okay, so again we will start with the help of turbulence modeling. Okay, so basically what happens actually in a turbulence modeling, my dear students, here you can see that here just 1 minute I will use a pen. Okay, just 1 minute you can hold and we will start again. So my dear students, you can see that here in this particular, you can see that my dear students, here you can see that in this particular figure, you can see that how a velocity profile is going to develop over a flat kind of a plate or flat kind of a surface. Okay, so let's start by considering the fluid flow over a plate. As shown here in this particular figure, you can see that the uniform velocity profile hits the leading edge of the plate and a laminar boundary layer begins to develop. Okay, the flow in this region is very predictable. After some distance, some chaotic oscillations begin to develop in the boundary layer and the flow begins to transition to turbulence. Okay, eventually becoming fully turbulent. So here you can see that when the fluid is trying to flow from this particular direction, you can see clearly here when the fluid is trying to flow from this particular direction over this particular plate. So this will be your leading edge, and you can see that how the velocity boundary profile is going to develop over here. Okay, after some reason, this particular region is dominated by the viscous forces. That's why we have a kind of laminar profile available here, laminar kind of a region which is available here, and the velocity boundary profile you can see here that after this laminar boundary profile, when fluid is passed out through some distances, some disturbances happening in that particular fluid flow regions means that the fluid particles are going to be move in different directions. There will be some now the viscous forces are reducing, hence the turbulences start creating. So in this particular transition region, the fluid flow is going to become a kind of a turbulent kind of a flow. So after that, you can see that we have another region, the last region towards the trailing edge of that particular plate. You can see that we have too much variations in the fluid particles when they are flowing in that particular fluid region. So we have a kind of a turbulent boundary conditions which we have available over there. Okay, so my dear students, as we talk about the profile or the boundary layer profile which are developing over any kind of a surface or a plate, so at the wall we can assume the velocity of the fluid particles related to the wall around is approximate to 0. Okay, after that we have some velocities are available in a layer, another layer of a fluid with just above your wall, which is known as a laminar sublayer, or you can say as a buffer layer. Okay, after that towards in when we will go in upward direction or in a vertical direction through y direction along the distance through the wall, when we move forward, we will have more velocities, and the turbulency will at that particular label, at that particular region, we will have more turbulency in that particular region. That is shown here as a turbulent region, means that towards when we will go in a y direction, we have more turbulent region in any fluid flow or regime, or in any fluid flow region, or in any fluid flow field. Okay, so now we will move to our next slide. So basically in the laminar region, the fluid flow can be completely predicted by solving a Navier-Stokes equations which give the velocity and the pressure field. So my dear students, what is the need of a turbulent model? What are the requirement of a turbulent model? As we can see that, as we can see in our last picture about the boundary layer profile over a plate, you can see that. So in laminar boundary layer region, the basically that particular fluid flow behavior in that particular region, we can solve it, we can find it by using a Navier-Stokes equations. Okay, as the flow rate and the Reynolds number when increases, the flow field exhibits small eddies, and the spatial and temporal scales of the oscillations become so small that it is computationally unfeasible to resolve them using the Navier-Stokes equations. Okay, at least for most practical cases. In this flow regime, we can use a Reynolds average Navier-Stokes equations or formulations, which is based on the observation that the flow field with respect to time contains small local oscillations and can be treated in a time average sense for 1 and 2 equation models. And additional transport equations are introduced for turbulence models, such as the turbulent kinetic energy K in that particular flow field. So my dear students, from this particular statement you can understand that, you can describe that when we have a kind of a laminar kind of a region available, we can directly compute all the fluid parameters like velocity and pressure with the help of Navier-Stokes equations. But when we are going to assume, when we are going to solve a problem related to computational fluid dynamics like in a turbulent models, we need to consider the fluctuation in that particular velocity parameters. Means that if you remember that, just go to your previous lectures about the Reynolds decompositions or the Reynolds stresses, where we are talking about when we are decomposing our velocity component with respect to the time, and we decompose our velocity component with respect to the time when we are taking the average velocity from that particular flow region, which is capital U is denoted, I think, and the fluctuated velocity, which is denoted by U dash. So when the velocity we are going to consider with respect to the time in that particular fluid flow region, in that particular fluid flow regime, so means that equation means that these are the additional parameters or the additional values we are going to consider. So for that purpose, we have RANS model in turbulent fluid flow phenomena, okay, which is known as a Reynolds average Navier-Stokes equation. So means that by using the RANS equations, and based on RANS equations, we have lot of turbulent models exist, which we are going to discuss in our next classes or in our next topics. Okay, so all we can say that all our turbulent models which are developed, they are already, and they are the basis of Reynolds average Navier-Stokes equation, which is a time average equations, and based on the times, basically we are going to consider the variation or the fluctuation in the velocity in that particular fluid flow region. Okay, so by using this we can solve the turbulency in any fluid flow region or in any flow field. Okay, so and in this particular equations we can add another transport variables which are not the property of the fluid. Again, I am telling you guys, these are not the properties of fluid, but again these are the very essential parameter while we are going to calculate any kind of a turbulence flow in any fluid flow region. Here is mentioning here about the K, which is a turbulent kinetic energy. Again, why we are talking about it? Because whenever Reynolds number is going to increase, the turbulency of course in that particular fluid flow is going to increase, and of course the turbulence kinetic energy will be more. So we need to transport that variable which is denoted here by the K. So we have to solve that K, turbulent kinetic energy. We have to consider it in that particular fluid flow region to analyze and to solve that particular fluid domain to get our results. Okay. Now we'll move to our next slide. What is the concept of a low Reynolds number when the Reynolds number is less or low in any fluid flow region? When the low Reynolds number models, it sounds like a contraction, since flows can only be turbulent if the Reynolds number is high enough. Of course, my dear students, you understand it very carefully that when the Reynolds number is going to be high, of course the turbulency in that particular fluid flow is going to be high. The notation low Reynolds number does not refer to the flow on a global scale, but to the region close to the wall where viscous effect dominate. Of course, when the viscous effects are dominating, where the viscous forces are dominating, of course, what conditions there on the boundary layer, what conditions on the when the fluid is going to interact with any kind of surfaces, you understand it very clearly, is that the viscous sublayer in the figure which is given above. A low Reynolds number model is a model that correctly reproduces the limiting behaviors of various flow quantities as the distances to the wall approaches to 0. Okay, so a low Reynolds number model must, for example, predict the K y tends to 0. Correct limit behaving means that the turbulence model can be used to model the whole boundary layer, including the viscous sublayer and the buffer layer. Why we are always talking about the turbulent model and the turbulent equations, and all these equations are used to solve your all engineering applications. Why? Because when we talk about a low Reynolds number, so my dear students, जब मेरा जो Reynolds number है वो कम होता है, that time means that we are considering to be a kind of a laminar region. We are trying to consider it as a sublayer region, viscous layer region, means that our viscous forces are dominating there. So इसकी हेल्प से लो रेनॉल्ड्स नंबर के जितने भी मॉडल्स हैं उनकी हेल्प से हम केवल एक लैमिनार का प्रॉब्लम ही सॉल्व कर सकते हैं, विच इज क्वाइट इजी टू सॉल्व इन एनी कंप्यूटेशनल फ्लूइड डायनामिक्स सिस्टम. ओके, बट व्हेन वी टॉक अबाउट ए बाउंड्री लेयर प्रोफाइल, व्हेन वी टॉक अबाउट ए फ्लूइड फ्लो रीजन, उसमें बहुत तरीके की हमारे पास लेयर्स हमारे पास होती हैं. वॉल के जस्ट अलोंग हमारी लैमिनार सब लेयर है, उसके ऊपर हमारी बफर लेयर है जिसमें हल्का सा फ्लक्चुएशन हमको मिलता है आपके वेलोसिटी में. उसके ऊपर हमारा जो ट्रांजिशन रीजन है, उसके ऊपर हमारा जो टर्बुलेंट पूरा रीजन है जहाँ पे हमारी वेलोसिटी मैक्सिमम हो जाती है. तो उस टर्बुलेंसी को उसको हम कैसे कैप्चर कर सकते हैं? हाउ वी कैन कैप्चर दोज डिफरेंट वेरिएशंस इन द फ्लूइड फ्लो रीजन इन डिफरेंट लेयर्स. हाउ वी कैन, from laminar viscous sublayers to buffer layers to turbulent region. So for that we need to develop such kind of a model which can capture all these variations of a velocity, either you can say pressure and all these things. For that purpose we have developed these turbulent model. Okay, so low Reynolds number is not successful to capture all these layers in a boundary flow. It will not giving you a systematic or a good results regarding that particular problem. Okay, so that's why we have developed, or the scientist or the researcher developed the turbulent models. Okay, my dear students, the most omega based models are low Reynolds number models by constructions, but the standard K epsilon models and other commonly encountered K epsilon models are not Reynolds number models. Now we will classify all these K epsilon and K omega later on. Some of them can, however, be supplemented with so-called damping functions that give the correct limiting behavior. They are known as Reynolds number K epsilon model. Okay. My dear students, low Reynolds number models often give a very accurate descriptions of the boundary layer. Very accurate. Often give a very accurate description of a boundary layer. The sharp gradient close to walls do, however, require very high mesh resolutions, and that in turns means that the high accuracy comes at a high computational cost. Of course, while doing a computational analysis, while we are performing a computational fluid dynamic analysis, we understand, we know that what are the requirements to solve that particular problem. Okay, this is why alternative methods to model the flow close to walls are often employed for industrial applications. Okay, we'll move to our next slide. Now, there is one of the very important concept and the fundamentals while we are talking about the boundary layer profile or solving the fluid flow behavior and over any kind of a surfaces. Okay, so that is known as a wall functions. So basically, what is the wall functions? The turbulent flow near a flat wall can be divided into four regions. You understand it very well. At the wall, the fluid velocity is zero, and in a thin layer above this, the velocity is linear with distance from the wall. Okay, this region is called as a viscous sublayer. My dear students, again you can understand it, or laminar sublayer. Okay, the layer which is just adjacent to your wall. Okay, now further away from the wall is region is called, that is buffer layer, where the little bit fluctuation in the velocity parameters are there available. Okay, in the buffer region, turbulence stresses are begin to dominate over viscous stresses. Of course, when the viscous forces actually are dominating up to the only viscous sublayers. Okay, that's why we have a kind of a velocity, they are almost kind of zero at near to wall. When we will go into the y direction, we will have the domination of a turbulent forces. Due to those dominating nature of a turbulent forces, we have a development of a turbulent stresses over that particular layer, which is a buffer layer. Okay, and it eventually connects to a region where the flow is fully turbulent, and the average flow velocity is related to the log of the distance to the wall. The average velocity in that particular region is to the log of the distance to the wall. That is a law of wall, which is a logarithmic law, which I have discussed in a previous lectures about this particular concept. Okay, now this is known as a log law region. Okay, even further away from the wall, the flow transition to free stream region, the viscous and buffer layers are very thin, and if the distance to the end of the buffer layer is delta, then the log law region will extend about away from the wall. That is the concept of a wall function. So it is very important while performing any kind of a computational fluid dynamics simulations, how to capture the wall, how we need to treat the wall treatment. It's very important when we will do a CFD simulations, when we will perform a computational fluid dynamics analysis, we will understand it, how to capture the wall, how to give the functions to wall, so that we can easily capture those boundary layers, those buffers layers, those sub layers, those laminar layers, those viscous layers in our problem. Okay, now move to next slide. It is possible to use Reynolds average Navier-Stokes model to compute the flow field in all four of these regions. However, since the thickness of the buffer layer is so small, it can be advantageous to use an approximation in this region. Wall functions ignore the flow field in the buffer region and analytically compute a non-zero fluid velocity at the wall. By using a wall functions formulations, you assume an analytic solution for the flow in the viscous layer, and the results models will have significantly lower computational requirements, and this is very useful approach for many practical engineering applications. If you need to a level of accuracy beyond what the wall functions or formulations provided, then you will want to consider a turbulence model that solves the entire flow regime as described for the flow low Reynolds number models above. For example, if you want to compute lift force, drag force on any object, or compute the heat transfer between the fluid and wall. Okay, so my dear student, that's why we have all these turbulents are available, so that we can easily capture all these things. So once you will understand these models and the applications of these different models, these different turbulent models in engineering applications, you can easily utilize these equations or these models to solve any computational fluid dynamics problems. Okay, now we'll move to our next slide. My dear students, as I already told you that we have a Navier-Stokes equations to solve a normal or kind of a laminar problem. But when we talk about Reynolds average Navier-Stokes equation, a time average base equations, which is used to solve different types of turbulent models, so we have different types of models are available based on Reynolds average Navier-Stokes equations. So RANS based turbulent model, we can see that. So the objective of the turbulence model for the RANS equation is to compute the Reynolds stresses. What are the Reynolds stresses? I already told you in the previous lectures, okay, which can be done by the three main categories of a RNS based turbulence model. That's why I'm always saying that these different types of models are known as RANS, Reynolds average Navier-Stokes based turbulent models. So what they are? First one is your linear eddy viscosity models, second is your non-linear eddy viscosity models, third one is your Reynolds stress models. Now we have one equations model and two equations model. These one equations model means when the driving parameters are one, and two equations model means that when we have two driving parameters are available. What they are, we will see in our classification of these turbulence models, that what are the models which are under categorized in the terms of one equations model, and what are the models which comes under the category of two equation models. Okay, so if we talk about two equations turbulence models, so two equations turbulence models are one of the most common types of turbulence models. Like K epsilon and K omega models have become industry standard models, are commonly used for most type of engineering problems. Okay, what they are actually we are going to discuss here. Two equation turbulence models are also very much still an active area of research, and new refined two equation models are still being developed. Two equation models include two extra transport equations to represent the turbulent properties of the fluid. How we are going to define that particular turbulent nature of the fluid, it depends on these equations, depends upon you how you are going to define the turbulentity up to maximum layer. If you are going to analyze the turbulent nature of the fluid flow in that particular region, you are of course going to solve that particular problem. Okay, this allows the two equation models to account for history effects like convection and diffusion of a turbulent kinetic energy. If I take an example of a K epsilon equation, suppose, let's say for an example, K epsilon equation, one of the very important equations which is used to solve a kind of a turbulent problem. Okay, the minor turbulent problems we can solve by using this particular K epsilon equations very easily. So what these two parameters means, K and epsilon, these two parameters here are available, that's why these two are driving parameters, that's why these we are saying that this is a two equation turbulent model. Okay, now these two parameters are not properties of fluid in any sense. These two are the parameter, you can say, from that particular flow region, means that K, which is known as a turbulent kinetic energy, and epsilon is known as a rate of dissipation. Yes, dissipation rate you can say, or specific dissipation rate you can see that. Okay, so one transport variable is K in two equation model, and one transport variable is epsilon, turbulent kinetic energy and specific dissipation rate. Okay, so actually the second variable, which is specific dissipation rate, can be thought of as a variable that determines the scale of the turbulence, which is known as a length scale. Scale of a turbulence means length of scale. Okay, K turbulent kinetic energy, you understand it very easily. I think the kinetic energy which is available in that turbulent flow region is a turbulent kinetic energy. And second, which is a specific dissipation rate, means that the mixing length scale or the time scale you can say, or the scale of the turbulence. Okay, where the first K is a turbulent kinetic energy. So these two parameters, these two variables are available in these particular equations. That is why we are saying that this equation is known as a two equation model. Okay, similarly my dear students, there are number of turbulent models are available based on RNS. So what they are, we are going to classify here. We'll move to next slide. We can see that we have a linear eddy viscosity models based on RNS. The first one is algebraic models. You can see that Seebeck-Smith models, Baldwin-Lomax model, Johnson-King models, and roughness-dependent models. Second is your one equation models, which is Prandtl's one equation model, paired with Barth models, Spallert, Almaraz models. Third one is your two equations models like K epsilon, K omega, and realizability. So realizability models, K epsilon models, and K omega models. So we have subsections of these like standard K epsilon, realizable K epsilon models, RNG K epsilon model, near wall treatment, Wilcox, SST, near wall treatment. So these are sub models of these two equations models are available. So when we will solve our problem in CFD domain, we will understand these equations that yes, what kind of a problem we can solve using these equations or these governing equations. Okay. Non-linear eddy viscosity model like explicit non-linear constitutive relations, V2F models and Reynolds stress models. And when we talk about large eddy simulations, LES, we have Sam-Gronsky, Lilly models, dynamic subgrid scale models, RNG LES models, wall adapting local eddy viscosity models, whale model, we can say that, kinetic energy subgrid scale model, near wall treatment for LLC models, DES, detached eddy simulations we have, DNS, direct numerical simulations we have. We can do turbulence near wall modeling, we can do turbulence free stream boundary conditions, we can do turbulence intensity, and we can do turbulence length scale. So my dear students, these are different types of turbulence models are available in our computational fluid dynamics domain. Some of them are in our syllabus, we are going to study that, we are going to understand that, and based on that we will going to utilize these equations on our computational fluid dynamics problem to solve any kind of a problem or a fluid domain. Okay, so I hope you understand it and revise it. So in next lecture we will do one turbulence model equations which is in our syllabus. Okay, so till then take care all of you. Thank you.